Hey everyone, and welcome. So, have you ever stopped to think about how a computer, something that really only gets ones and zeros, can possibly make sense of a complex programming language? Or, even start to understand human language? Well, today, we are unlocking that secret, and it all comes down to this incredibly powerful idea known as a grammar.
And really it all boils down to this one fascinating question, right? You and I, we can create and understand a totally limitless number of sentences we've never even heard before. So how on earth can we code that infinite ability into a machine that is by its very nature finite? That is the exact puzzle we're going to solve today.
So here's our game plan. We're going to start with the absolute basics, the real ground floor. Then we'll hit a major problem, introduce the super elegant solution, see how we can actually visualize it, and then finally, we'll dig into what happens when the rules get, well, a little fuzzy.
Okay, let's just dive right in. If we're going to build a language from the ground up, we need a few key ingredients. And it all starts with the simplest possible element you can imagine.
First up, we've got the alphabet, which we show here with the Greek letter sigma. Now, this is just the collection of all the valid characters we're allowed to work with. Seriously, think of it like your box of Legos. For our example, our entire universe of symbols is just the letters A and B. That's it.
So once you have your alphabet, you can make a word, or what we often call a string. You just take symbols from your alphabet and stick them together in some order. It can be any length at all, including, and this is important, a length of 0. We call that special case the empty word, and we use the Greek letter epsilon to show it. It's basically a way of saying that nothing is also a valid, if, very short word. And that brings us to the final piece, a language. A language is really just a specific collection of these words that all follow some shared rule. It could be a super simple, finite list of words we picked out, or, and this is where it gets interesting, it could be an infinite set, like the language of every single possible word that happens to start with the letter A. Okay, so these basic ideas lead us straight to our first huge problem. If a language can be infinite, how in the world do we define it for a computer? I mean, you can't just hand it a list of all the words, right? Because that list would literally never end.
This right here is the core challenge that a huge part of computer science is designed to solve. Just think about English for a second. You couldn't possibly write down every single valid English sentence in a giant book to teach a computer. You'd never ever finish. We need a much smarter way to do this.
And this quote from our source material just nails it. An infinite language, by its very definition, needs something more than just a big list. It needs a generative method, a kind of blueprint for creating words, not just a warehouse for storing them. So what is this blueprint? Well, it's a set of rules we call a grammar. And we're going to look at a really powerful type called a context-free grammar. All context-free means is that the rules for swapping out a placeholder don't care about what's around it. This is our machine, our engine, for generating every valid word in a language, and, just as important, only the valid ones. So every one of these context-free grammars has these 4 parts. Terminals, that's just our alphabet again, the actual letters. Variables are just temporary placeholders we use during construction. The start symbol is, you guessed it, the special variable where every single word begins its life. And then, the most important part, productions. These are the substitution rules that tell us exactly how to swap out variables to build our words. Okay, so that's all the theory, but how does this rulebook actually, work? Well, the process of using these rules to create a word is called a derivation. It's kind of like following a recipe, one step at a time, to bake a cake. Let's try to generate the word ABAB. We always start with our start symbol, S. Then we apply a rule. Let's say S can become ASB. Okay, so now we have ASB. But wait, we can apply that same rule to the new S in the middle. That gives us AASBB. We're almost there. Finally, we use another rule that says S can become nothing. That's our friend epsilon. And boom, we're left with ABAB, a perfectly valid word in our language. Now, that step-by-step process we just did, it's not just some flat list of steps. It actually creates a hidden structure, a kind of hierarchy, which we can actually draw out and see. And this takes us from just a simple recipe to this beautiful visual blueprint.
And this visual representation has a name. It's a syntax tree, or sometimes a parse tree. The start symbol, S, sits at the very top, at the root of the tree. The branches show the rules we decided to apply, and the leaves at the very bottom, if you read them from left to right, spell out our final word.
So why do we care so much about these trees? Well, because if you can successfully build a syntax tree for a word, you have just proven that the word is grammatically correct according to your rulebook.
And this is exactly what a compiler does with the code you write. It builds this tree to understand the structure of your program, catch silly errors like a missing parenthesis, and even figure out how to optimize the final program.
But, and there's always a but, here's where things get really tricky. What happens if a single sentence can be built using more than one completely valid syntax tree? Well, that leads to a really critical problem.
We call this ambiguity. And an ambiguous grammar is basically one where the rules are a little too loose, allowing for multiple different structural interpretations of the exact same sentence. And for a computer that needs things to be precise and predictable, yeah, that's a really big deal.
Our own natural language is just full of ambiguity. Take this sentence, for example. I saw the man with the telescope. So, who has the telescope? Did I use the telescope to see the man? Or did I see a man who just happened to be holding a telescope? Both are perfectly reasonable ways to understand that sentence.
And right here we can see why it's ambiguous. Each of those meanings corresponds to a totally different syntax tree. In one tree, the phrase "with the telescope" is attached to the verb saw. In the other, it's attached to the noun man. Two different trees, two different meanings, but only one sentence.
This need for precision is exactly why it's so important to be clear about our definitions. And this brings up a common point of confusion I want to clear up. The empty word, epsilon, is a real thing. It's a string that just happens to have no characters. So a language containing only that word is not empty. The empty language, however, is a set with absolutely nothing in it. See the difference? One has a single, tiny thing in it, and the other is truly empty.
So let's bring this all back home. Why does any of this actually matter? Well, because these grammars are the invisible engine running behind so much of our modern world. They are the official blueprint for almost every programming language out there. They're what compilers use to understand the code you write. They are a foundational concept for the AIs trying to make sense of messy human language. And ultimately, they're the incredibly elegant, finite solution to that problem of infinite expression.
And that leaves us with one final thought to chew on. We've just seen the complex, rigid, and very precise machinery a computer needs just to process language. It really makes you wonder about our own brains, which handle ambiguity, context, and nuance almost effortlessly. What kind of incredible grammar engine is running inside our own heads?